Okay guys, today what we're going to be talking about is energy and how it's conserved and the different ways we can use it. So first of all, energy, just like momentum, is conserved. So whatever your energy is initially, that should equal your energy finally. Now, a little caveat to this, a little thing that's not necessarily always true, is that a certain type of energy, initial, like kinetic energy, may not be conserved. So like kinetic energy initial, it does not have to equal kinetic energy final. But if you have if you have the two types of energy, potential energy initial, and then you add it to the kinetic energy initial, that should equal the potential energy in the end plus the kinetic energy in the end. All right? If you lost any energy, you would add that in here. So like you can lose energy to heat and sound and whatnot, and if you lose that energy, it goes in at that point. Okay, so the next thing we need to look at is what happens whenever we, what types of energy are there? Well, there's three major types of energy, all right? The first major type of energy is gravitational potential energy. So we're going to call that GPE, gravitational potential energy. And gravitational potential energy is based upon how high you are. And so since it's based upon how high you are, it's equal to your mass times your gravity times your height. Okay? So if you're a certain height up and you have a ball held there, the amount of potential energy due to gravity that it has is equal to the mass of that ball times g, and remember that g is equal to 9.8 meters per second squared, and sometimes we just call it 10 meters per second squared for easy math. So it's equal to mass times 10 times whatever height it's at. And obviously, gravitational potential energy works in such a way that the higher you go, the more energy you have for gravitational potential energy. Okay, the next type of energy is kinetic energy, and kinetic energy is the energy of movement, and kinetic energy is equal to 1/2 mv squared. Okay, so that's kinetic energy, 1/2 mv squared. And so kinetic energy can occur anytime an object is moving. If an object is not moving, there is no kinetic energy. So if you're just holding a ball above the ground, there's no kinetic energy. But anytime anything's moving, it has to have some kinetic energy. The last type that we'll talk about is the elastic potential energy. So elastic potential energy, EPE. And elastic potential energy is the energy stored in a spring or a rubber band or something that stretches or compresses or anything like that. That's the energy that is there. So we have this formula 1/2 kx squared for it. Okay, this is a really confusing formula because we're just not used to seeing it. So let me just briefly go into what each piece of it means. Okay, so the K is the spring force, the spring constant. And the spring constant is just a constant that tells you basically how strong the spring is. All right, and then X is the distance that you pulled that spring or pushed the spring in. So if it's a compression spring, you would push it in. If it's a rubber band, obviously you'd have to pull it. And that's the distance from normal. So the distance from where it would be if it was just sitting still. All right, and obviously, if you've ever messed with a rubber band, you know that the farther you pull it back, the more and more energy you get. And so that's the reason the X is squared there, because the further you pull it back, that's the reason it's involved in the problem. The further you pull it back, the more energy you get. All right, so the thing that we need to know now is that all of these energies are conserved. So if we wanted to, if we're working with a problem that involves all of these things, then the elastic potential energy plus the gravitational potential energy plus the kinetic energy, all of these are the initial ones, would have to equal all of the ones at the end. Okay? Now, this formula that I'm writing right now, you are rarely, if ever, going to have to see everything at once. In most cases, all of these but a few will cancel out. Okay? So most of the time, kinetic energy initial will be 0, or elastic potential energy will be 0, but like, you need to know that all of that could happen. And then don't forget that we also have to add in the possibility of there being energy loss. Again, it'll be very explicit if energy is lost. It will say, energy was lost. Alright, the last thing I want to talk about right now is the work energy theorem. So the work energy theorem is it sounds really complex, but in fact, all it is this. First of all, work is equal to force times distance, or rather displacement. So when you're doing work, it's equal to whatever your force is times however much you've displaced the object. And so this is tricky sometimes, because technically if you just lift an object and put it back in the same spot, you didn't do any work in terms of how much physics you did, right? So physically you didn't do any work in terms of academic physics, I guess. There was no work done. Like if you go to the weight room and lift weights, you're not doing any work. That's kind of annoying to some people, but if you successfully complete all your lifts, you put it back in the same spot. So you didn't really displace anything, so you didn't do any work. So if you came into my classroom and told me about all the work you did, I would tell you didn't do anything, because unless you failed. If you failed, the bar would be displaced and you would have done some work. But in general, we can just say work is equal to force times distance. Well, if we want to change the energy of the system, remember I said energy was conserved? Well, it's conserved as long as there's no outside forces. If there is an outside force, we have to use the work energy theorem, and the work energy theorem states that the work done on an object will equal the change in kinetic energy. So if you do work on an object, you will change the kinetic energy of that object. All right? And this is the total work done on that object. So, for instance, if you're lifting an object, you're having to fight gravity and lift it at the same time. So the work being done by gravity to resist your movement will be canceled out by the work you're doing to resist gravity. And so any speed that you gain will have the forces and the work that you're doing to counteract gravity taken out because it's the work total. Alright, and I can get into more depth on this in another video, but I just wanted to show you basically what was going on here. Alright, so this is, again, the work energy theorem. Then we have the theory of the conservation of energy. All of these energies have to be conserved throughout the entire process here. And then we have elastic potential energy, and this is the energy of a spring or a rubber band or something like that. And then we have kinetic energy, and kinetic energy is the energy of movement. If something is not moving, it has no kinetic energy. And lastly, we have gravitational potential energy, and gravitational potential energy is the energy based upon how high you are off the ground. Alright, you have all the formulas for this stuff now, and so hopefully you are ready to get going on your problems with energy.